De-icing and anti-icing chemicals play a significant role in ensuring Iowa's road network remains ice-free and safe for the traveling public throughout the winter months. In order to fully understand how de-icing chemicals work, we will need to review some basic chemistry. Water molecules consist of an oxygen atom with two hydrogen atoms attached. In this asymmetrical molecule, the two hydrogen atoms have a positive electrical charge, while the oxygen end of the molecule is negatively charged. Water molecules exist in three states of matter: gas, liquid, and solid. In their gaseous state, water molecules move so fast they bounce off each other and never become attached. In their liquid state, water molecules are moving too fast to stay locked into crystals, but slowly enough to be attached to each other. In their frozen state, water molecules are locked together in hexagonal crystals. Individual molecules are vibrating, but not fast enough to break out of the crystal. The positive hydrogen atoms are attracted to the negative oxygen atoms, which holds the crystal together. Now let's look at how de-icing chemicals interact with and melt ice crystals. This is what a salt or sodium chloride molecule looks like. It is made up of one positively charged sodium ion and one negatively charged chloride ion. When salt is applied to ice and there is moisture or water present, the sodium chloride molecule begins to break apart into positively charged sodium and negatively charged chloride ions. The negatively charged oxygen ions of the water molecules are attracted to the positively charged sodium ions of the salt. Similarly, the positively charged hydrogen atoms of water are attracted to the negatively charged chloride ions in salt. Because water molecules are more strongly attracted to sodium and chloride than each other, they unlock from their ice crystal formation even at temperatures below 32 degrees Fahrenheit. This attraction destroys the structure of the ice crystal and dissolves the salt, resulting in a saltwater solution or brine. De-icing and anti-icing chemicals like sodium chloride work by lowering the freezing point of water. The adjusted freezing point depends on the concentration of salt in the solution. This is illustrated by the phase diagram shown, with temperature on the vertical axis and solution concentration of sodium chloride along the horizontal axis. The diagram shows the temperature at which various concentrations of brine change from liquid to solid. For example, at 20 degrees, a 10% solution of sodium chloride could melt ice. The freezing point declines to -6 degrees at a concentration of 23.3% sodium chloride. -6 degrees is sodium chloride's maximum freezing point depression, or eutectic temperature. As the concentration increases beyond 23.3%, the freezing point of the chemical rapidly increases. Each de-icing chemical has its own special characteristics. The eutectic temperature of calcium chloride occurs at -60 degrees at a 29.8% solution. Sodium chloride and calcium chloride are called freeze point depressants because they depress the freezing point of water. This is what makes them so useful in winter maintenance operations. The phase diagram best illustrates this and provides important principles for applying salt or brine. When applying material, adjust the solution concentration so that when plotted with the roadway temperature, it falls into this green area. Your supervisor and experienced operators can assist in determining the appropriate amount of material to be applied per lane mile. If the solution concentration and temperature are in the red area, the solution concentration will not be high enough to melt all of the ice on the roadway. If the combination of the concentration of solution and temperature falls into the blue area, the mixture you apply will have little to no effect until more moisture is present to dilute the concentration. The yellow area shows that with temperatures below -6 degrees, melting will not take place at all. Salt will remain on top of the ice until the pavement temperature warms. De-icing and refreezing is a continuous battle that you will have to endure in any given event. Appropriate material application will ensure material concentrations do not dilute to a point that they will become ineffective. Let's take a look at a specific example involving material applications using the phase diagram. Let's say you apply brine to an ice-covered pavement that is 20 degrees. As long as the temperature remains at 20 degrees and the brine concentration is at 23.3%, you are in the green area and melting is going to occur. However, as the ice melts, the brine is diluted. As soon as the concentration drops below 10%, you begin moving into the red area, and the melted ice will begin to refreeze. Even if the brine concentration remains at 20%, but the temperature begins to rapidly drop, you can see that refreezing will occur as soon as the pavement temperature reaches 3 degrees. Take time to fully understand the phase diagram, because it applies every time you use de-icing chemicals. When a solid de-icer like salt is applied to an ice-covered pavement, it must first dissolve and become into a solution before melting can occur. Moisture can come from pre-wetting the salt or from moisture on the roadway surface. Dilution of solution must always be considered when applying de-icing chemicals. Dilution occurs during the melting process and when additional precipitation falls. Guidelines are provided that give optimal application rates for a given set of weather conditions. For each event, work closely with your supervisor and other operators to determine the correct type and amount of material to be applied.